So this is an extra little video for chapter 1 of the AS Pure Maths course, going with this textbook here, the Edexcel Pearson. And it's to go on the end of my playlist because I've talked about how to do everything in this chapter, but with the surds we've not actually stopped and talked about surds yet. So let's just take the example, the simplest one, square root of 2. So square root of 2 is approximately equal to 1.4142135562. Okay, so if we draw ourselves a number line that's going to go 0, 1, 2, well this is 1.414, so here's 1.5, square root of 2 is somewhere sort of here-ish. Okay, that number is sort of here-ish, and square root of 2 is sort of here-ish. Okay, now if all you're worried about is a measurement, so let's say you are an engineer and for some reason you want to make a right angle triangle, which is 1 meter this side, 1 meter this side, and you need to get some special material cut which is going to make the hypotenuse of your right angle triangle, well that needs to be square root of 2. You know, by Pythagoras theorem, the length of that is square root of 2. Now if you're an engineer, this will do, won't it? If you know that number, you know, you get your ruler out or you get your measurement device out and you measure it as accurately as you want to. So if you need it to the nearest centimetre, then you do it 1 metre and 41 centimetres. If you need it to the nearest millimetre, then it's 1 metre, 41 centimetres and 4 millimetres. You can get down to 1/10 of a millimetre if you use the 2, and 100th of a millimetre here, 1,000th of a millimetre here, 1/10,000th of a millimetre by the time you get to here, right? So if you're an engineer, really, that is close enough. If you need to make something really accurately, the square root of 2, a bunch of decimal places and you're sorted. So if you're a physicist, if you're an engineer, if you're dealing with real-sized numbers, if you're doing applied maths on the mechanics part of this course or the statistics part, square root of 2 may as well be the same as this number. The difference isn't important. But here's what is important. On this number line, let's think about what we mean by a number. A number is just a point on the number line. Okay? Now, the square root of 2 is an irrational number. That means it can't be written as if you write it as a decimal, it's non-recurring and it goes on forever. Now, I'm not going to get drawn into all the interesting things with that, but let's just take that fact from me at the moment on trust. You can look it up or ask your teachers if you're interested in more about that. But look, trust me, if it's a decimal, it goes on forever and it's not recurring. That means that square root of 2 is not equal to what I've just written down there. It's equal to a much longer decimal. Now, it's very, very close to what I've written down here. But what we're interested in as pure mathematicians, for the blue book for Edexcel, not the brown book, the blue book, we're interested in numbers. We're interested in studying numbers and the properties of numbers. What do we mean by a number? Well, a pretty good sort of working definition is it's a point on the number line. So if a number is a point on the number line, having two numbers that are close on the number line, but not actually the same thing, well, they're not the same thing. If I'm interested in the square root of 2, if I'm interested in an algebraic answer, which gives me the square root of 2 as an answer, if I've got if I've got something like, well, x squared equals 2, so x could be root 2 or x could be minus root 2, it's important as a pure mathematician that those are my answers. That is not the same. It is no good to say the answer is close to 1.41421355 and the other answer is close to minus 1.41421355. As a physicist and engineer, close to will do, because you can get as close as you like. As a mathematician, the difference between this part of the number line and this part of the number line is really important. They are different points. As an engineer, a physicist, a computer scientist, most of the time, it's fine. They're different points, but they're so close that we don't care about the difference. As mathematicians, we care about the actual numbers. We care about the abstract sort of philosophical concept of what the numbers are. When I square this number, I get 2. When I square this number here, the decimal, I get something really close to 2, but not exactly 2. Okay? So this point on the number line and this point on the number line are different. So in pure maths, we are going to leave things as simplified surds. What's important to us is the numbers, how they fit together, what the relationship between the different numbers is. Say you're asking for an answer and being told, well, it's close to this. If I said what's 2 and 2 and you said, well, it's close to 4.00000001, that's not a good answer, is it? Right? 2 plus 2 equals 4, and that's the exact answer. In maths, we care about the difference. In engineering or an applied maths, you usually don't really care about the difference. If in engineering I say, right, I've got a 2 meter long length and another 2 meter long length, how long are they together? Then knowing that they are close to 4.00000001 is fine, because what you need to know is that if you put those two things together, then they're big enough to, I don't know, fit across this gap and make a bridge or whatever it happens to be, right? We're not dealing with, in pure maths, the practical side of things isn't important to us, the philosophical side of things is, right? So there's my little rant about why it's worth simplifying surds. The practical help that will be to you on this course will be that if you're thinking like a pure mathematician when you're doing any of these questions, you won't accidentally give your answers as decimals. And on some of the answers on the exam, they will knock a mark off if you don't give a simplified surd and you give a decimal. So you'll avoid your calculator, you'll go for simplifying surds and using the algebra to simplify the surds, and you won't trip up and lose marks. But really, the more important idea is that you're thinking like a pure mathematician, and you're realising the difference between pure maths and applied maths and physics and engineering and all those other things. Okay, that's the end of chapter 1. And next thing in the playlist will be chapter 2 when I get around to doing those.